Hello and welcome. This is the first video in a new series I'm doing about modeling the boost converter. So thanks for joining. Actually, more emphasis is going to be put on the techniques used than the boost converter itself. So what I'd like to really get through is state space modeling, sample time, all the way into discrete modeling. So state space through the small signal model of the circuit. As a caveat, I'm not really sure if sample time is the right word choice. I don't know if that's an actual term. That's what I'm calling it. Sample time to me is the equations that result from actually solving the state space equation. I can go more into that when we cover it in a video. But yeah, I'd like to get through those techniques. Those are more advanced techniques. So actually today specifically what I'll do is go through the average model in the small signal circuits so that when we get to the more advanced stuff, we actually have a point of comparison. And then as a side note, this PDF is available for download. If you look in the video description, you can download this PDF. It's got obviously the circuit topology, some waveforms, the intervals, and then it also includes all the stuff I plan to go over in the video series. So averaged and small signal circuit description is shown here. This is what I'll go over later in this video in a few moments. And then state space will be in a different video. Sample time description will be in another video, and then discrete time. And then finally, we'll probably go and do some comparison, maybe look at some MATLAB code, that type of thing. But if you want to download this, it's in the description. So without further ado, we'll jump straight into the average model derivation. Okay, so let me start by saying that if during any portion of this you need to pause the video, feel free to do so. I'm going to try to move quickly so that the video is concise, so feel free to pause. But what I've done here is start by including a picture of the schematic, a picture of the circuit, and then pictures of both intervals, D and D prime, and then I've also got the waveforms included here. So what we'll do is we'll start by looking at the D interval, and we'll write the voltage equation. VL equals input voltage minus the voltage across the parasitic inductor resistance. And then we'll look at the current equation, and in the D interval, it's just the capacitor current is equal to the negative output current, which we'll write as V out over R out. Then we'll look at the D prime interval, and we'll write those equations again. For the D prime interval, it'll be the inductor voltage equal to the input minus the parasitic minus the output voltage, and then we'll look at the current equation, and that'll be the capacitor current is going to be equal to the inductor current minus the output current. Now we'll do the averaging step. That's cap charge and volt second balance. So we'll consider that the average inductor voltage is going to be equal to the addition of the D interval and the D prime interval. So that's D times Vn minus ILRL plus D prime times Vn minus ILRL minus V out. And then the same for the capacitor. D times minus V out over R out plus D prime times IL minus V out over R out. Next, what we'll do is insert small signal terms. They're the hat terms. So for every variable x, you'll have some steady state variable I'll call capital X, and then some small signal term, x hat. So if we take the inductance equation that we've just written and we add all these hat terms, that's going to give you IL plus IL hat, D plus D hat, same for Vn, and then for D prime you'll actually have 1 minus D plus D hat, and you can take that entire equation and then multiply all the terms out and get this larger expression. So what I've done in this larger expression is isolate the single hat terms, but from a larger perspective, what we're doing is any double hat terms where I have a hat variable times another hat variable, I'm going to eliminate those. This is the linearization approximation. Then we're going to group the single hat terms like I've done in this equation. And then in a second, I'm going to show you we'll group the DC terms as well. So this again is the single hat equation, and I'm just going to start eliminating terms. So now we can begin simplifying. We will reduce this down and then reduce it down one more time by combining these V out hat terms. And then we'll write the DC terms into an equation of their own. And at this point, what you have is an averaged small signal equation and an averaged DC equation. And both of these equations that I've just underlined in yellow come from the volt-second balance equation. So now we'll repeat the process and come up with two more equations. I'm skipping some of the work here that come from the cap charge equation. And at the end of this, we'll have these four equations, two of which are average small signal and two of which are average DC. To continue the analysis, we'll pull these four equations over to a new sheet, and we'll create two equivalent circuits out of the small signal equations. You can see the voltage equation here is written as a loop in yellow, and then the current equation is written with each element in parallel. And then the DC equations we're not going to use for this section, so you don't use the DC equations for the small signal analysis. We'll take the two equivalent circuits that we just wrote and we'll combine them into one equivalent circuit. And where we combine these matters. So you'll notice that we combine them where the V out hat node in the yellow equation matches the V out hat node in the orange equation. And the IL hat current matches the current that will be flowing through the yellow equation. And the transformer, the equivalent transformer we use to combine them is a function of D prime, which is the value that both the V out hat and IL hat are multiplied by in each respective equation. So this idea of a small signal transformer is it's not a literal transformer, but it carries the same principles as a transformer in the sense that voltage and current here in the small signal sense are changed as parameters travel across it. We can then reflect impedances through that transformer and get this final equivalent circuit that we see here that I'm outlining in red. And then we can begin finding the controlled output transfer function, which I'll call GVD. It's a function of S, and what it shows is how the output voltage V out hat is affected by a change in duty cycle D hat. And to do this, what we have to do is set Vn hat equal to 0. And then after we've set Vn hat equal to 0, we'll use superposition, meaning that at first we'll set V out equal to 0. Note that that's not V out hat, that's just V out. We'll write the equation for the circuit there, and then we'll do the other side of the superposition where we set IL, again, not hat, equal to 0, and we'll write that circuit equation. We can combine the two of those. Superposition allows us to add those two effects together to get GVDS, and then what I've done here is just simplify the circuit so that finally you get GVDS is equal to V out hat over D hat equals this expression here. The last thing we'll do is readdress our DC equations. I'll just rewrite these in terms of Vn and V out, or rather as D prime is a proportion between the output voltage and the input voltage. And then finally, to wrap up this averaging analysis, we can just say, hey, these are DC equations and this is our controlled output transfer function. And for this video series, we'll use this as a reference to compare to these other more advanced models as we proceed through the series. All right, so for the last part of this video, you can see we've switched gears a little bit. I've got a MATLAB code opened. This is a simple little code that I've written, so I'll show you what it's about. First, I've chosen circuit parameters here. So I needed values for L and C, the parasitic, input voltage, etc., so that I could actually run simulations. These are pretty arbitrarily chosen. I've not optimized or anything crazy here. State space we're going to skip for now. This is what we've just worked on, so the average model. So this equation right here returns the DC value of inductor current. This one returns the output voltage, and then this is the output power, and then the rest of this is just a print statement. So when I run the code, it'll make it easier to look at. and understand. Here what I'm doing is approximating the linear ripple for the passives. So this is the inductor current. What I've done is take the D interval time, so that's D, the ratio, times the period, and then the voltage applied to the inductor during that time, which is Vn minus the voltage across the parasitic divided by the inductance. And that'll give us the ripple current in the inductor. I've done the same thing for the capacitor to get the ripple voltage. For either of these, you could actually use the opposite interval. So here I could use D prime, or down here I could use D. The value of this equation is exactly the same as the value of this equation, except this one is negative. That's because of volt-second balance, cap charge balance. The system's in steady state. So what I did for each of these was just choose the interval where the value is returned, the positive value is returned. And then down here, for all of this is just a figure to kind of illustrate all this stuff and make it easy to look at. So let me run this. So up here you can see the average steady state values. We've got almost 3 amps in the inductor current, 16 volts at the output, and about 26 watts of output power. And then let me drag this figure over. So these are the average DC values, and then the ripple waveforms applied around those DC values. So at the top you've got capacitor voltage, and then right here is inductor current, so that's the DC value, and then the ripple current around that based on our calculations. And then down here for reference I have the low side gate. So when the low side gate is high, you're in the D interval, and when it's low, you're in the D prime interval. So it's just a reference. Anyways, that'll pretty much wrap up this video. Again, this has been a really short, really concise overview of how to derive a boost converter using average models. You know, we went through the DC values, we did the small signal stuff, I showed the ripple here in the MATLAB calculations. So this mainly, again, is just going to be kind of a launching point for more advanced techniques in subsequent videos. So I hope it helps me, guys. I appreciate you joining me, and we'll see you in the next one.